Right, so in this video we're going to look at the Von Gogh APU and the position this could have in AMD's APU lineup. Of course, whether at all it makes sense for AMD to release it. We're going to look at this from two aspects. Firstly, the die area, and then secondly, we do a power analysis to get some approximate numbers of how it would perform. So yeah, what is Van Gogh, or what will we assume Van Gogh to be at least? Zen 2 APU, so 4 cores with single CCX, that would be, and then with RDNA 8 CUs for the GPU side. This RDNA config was leaked previously in early last year, I think. When was this? 6 months ago. So the RDNA config was leaked some while back in Reddit here, and we see the number of shader arrays per shader engine is interestingly it's different than any of the other RDNA configs. This might be necessary so that they can scale this architecture down to this 8 CU size, because all of these other ones are larger. This would be a 12 CU, this one here, and then all of the other configs are 20 CUs for Navi 14 and then 40 CUs and up for the other ones. So this is a little bit of a look at just the architectural balance might be different. It might be necessary to do that just to scale down to a smaller size like this. So yeah, firstly the die area analysis, and the conclusion here is really that the die area of Van Gogh would not be much smaller than Renoir. And the reason for this is simply that the main place you'd save die area, which would be the core count, going from 8 to 4 cores, would be only a very small reduction. Based off Wikichip's numbers for Renoir, the CCX should be around 19 millimeters squared. So this is a 4 megabyte of L3 CCX. For Matisse and the Epic chips, they of course used the 16 megabyte of L3 config, and this comes out to 30 or so millimeters squared. So I'm not 100% sure on this 19 millimeters squared number, because it's derived off calculations of the core minus the L3 area and then plus 4 megabytes of L3. So it doesn't count for the other components within the CCX. So it might be slightly larger than 19 millimeters squared, but I wouldn't expect it to be larger than 25 or so, and that would be quite an extreme case. I think 25 millimeters squared for the CCX. So Renoir is 156 millimeters squared, so a 20 millimeters squared reduction is only about 10%. So the other place we might save area is changing the GPU out from Vega to RDNA, but actually here we find that RDNA is actually slightly larger per CU, at least in the existing configs we know of. RDNA is slightly larger than Vega. And so to do this comparison, I used Vega 20, so that's a 7 nanometer chip for the Radeon 7, and Navi 10. The reason I used Navi 10 instead of one of the RDNA 2 chips is because the L2 cache adds quite a lot of size. If you compare Navi 10, so 40 CUs RDNA 1, to 40 CUs RDNA 2, so that's on Navi 22. Navi 22 has quite an increase in die area for the same CU count. And you might see from some of the performance testing, I think Hardware Unboxed did at the same clock speed, Navi 10 and Navi 22 perform about the same. So the comparison when you take Vega 20 CUs, Vega 20 with 64 CUs, you scale it down, we get about 207 millimeters squared for the 40 CUs. So this suggests Navi's die area is actually around 20% larger. Now this is of course a very crude comparison. First of all, the Renoir implementation might be different from Vega 20. It's probably quite different because they're, these chips are for a very different purpose. The scaling isn't proportional to CU count anyway. So as we talked about earlier, I said the shader array config. It's only a single shader array per shader engine. This changes some of the balance. We also have only 4 working group processors, so that's the dual CUs essentially per shader array instead of 5. The render backends 2 rather than 4, so all the scaling just sort of changed. The architectural balances are just different. And then that's not even counting for fixed function units and various other parts that don't scale with CU count. Some of these need to actually be the same, regardless of the same area, regardless of how many CUs you have. And of course, Vega 20 has a different memory interface than Navi 10, being HBM, of course. But if we just go with those numbers, we'd see an 8 CU would give us an 8 CU size of approximately 40 millimeters squared and about 50 millimeters squared for Navi. I'd say to make a safe conclusion, I would guess that these are going to be around the same size GPUs. I'm inclined to believe that RDNA would actually be larger, but I think it's quite difficult to prove that. But in either case, if we assume that the GPU is the same size, the CCX that you cut off is only 20 millimeters smaller. So you only save around 10%, 12% die area. So that's not really a worthwhile thing to do. AMD, for example, did the Dali APU, which is the 2-core variant of Raven Ridge, I think. So that's a much smaller die area, and that's been used in sort of a budget low end designs. So where they want a small die area just to make it cheaper to produce. And of course, if we're looking at this isn't a big die area saving, so it's not actually much cheaper in terms of silicon cost. So then let's look at the power comparison. First, I'm going to look a little bit at some theory behind this. And so this is the clock speed curve. So here we have the clock speed on the x-axis and the power draw on the y-axis. And basically the blue line is an approximation of sorts of how you would see the power draw of a single core increase with clock speed. And even at very low clock speed, our power draw can never be 0. This is just static power. Just having the thing on will draw a bit of power. There's going to be leakage currents. The circuits just need to operate as well. And then there's of course the dynamic power, which is the actual power taken to switch the circuit, and that will of course increase as you go faster. And of course, when you go faster, you'll need to have the clock speed, the voltage will need to be higher, so the power draw increases exponentially at some point. So we end up with basically 3 regimes. We have a peak operating efficiency somewhere in the middle here. There's a balance between the static power and the dynamic power. And then at the low end, we have a static power dominated regime, so the clock speeds are quite low, so the static power dominates, and then if we go very high, the dynamic power dominates because we need to drive up the voltage to keep the clocks. So essentially, as we move from a very low clock speed up to the middle, we get a higher performance and we get higher efficiency as well. And if we go too far, we'll get more performance, but our efficiency will taper off, and at some point we won't be able to increase the performance anymore. So what's important in this? Well, these APUs are of course running at, one of the purposes of an APU you want to do is at the 15 watt power envelope that Renoir runs at, you really want to maximize your efficiency. You don't want to waste power if you don't have to. So for example, if we put too many cores on an APU, we put 16, 32 cores for a stupid example, all of the cores would be running really slow and we'd be stuck in this static power dominated regime. Now, if we take two little cores and we have to clock them fast to get the same performance. Now, or well, not clock them fast to get the same performance, but we have one core, say, and we want to use up the whole 15-watt power envelope with that single core. Well, you can almost do that with Matisse, for example. You know, a 3600X, you could probably get the power draw per core to be around 15 watts, but you're only going to be getting a little bit more performance out of that. You know, that's only one core running at 4.2 gigahertz or so. And if we look at the numbers for Renoir, the per core power draw at 15 watts is about 1.4 watts, and at this power draw we're running at a clock speed of around 2 to 2.3 gigahertz. So going into these numbers, basically what I took was I looked at some of the reviews for the 4800U, and TechSport has some useful numbers where they've tested it both in the 15 watt and the 20 watt power configuration, and then the benchmark I chose for this was just Cinebench R20, and the reason I chose this is just a relatively consistent benchmark for looking at the performance at different clock speeds, because it just scales very consistently. Now, when we look at the 15 watts versus 25 watts, we see that we reduce the power draw to 60%, but the performance we get is we get about 85% of performance. So the 15 watt config here is actually more efficient than the 25 watt config, and at that config level we'd have around 4.1 watts per core, so a total core power of about 11.5 watts. So our estimated on-core power, so this will be the GPU, the Infinity Fabric, the memory controls, whatever. This will be 3.5 watts, and this is based off some numbers I got from several other users using Renoir laptops, and some notebook check numbers, and they essentially showed, when running some stress tests, the power per core drawn. So that's where this number comes from. So I would assume that that Van Gogh, that Renoir at 15 watts is somewhere around the peak efficiency. So on this curve, it'll be somewhere here. And the reason I think it's quite safe to make this assumption is because AMD actually considered running Renoir as a 6 core, but because they had the power envelope, they could increase that to the 8 core. And one of the reasons, of course, you would want to keep it at 6 cores is because you don't want to have to clock yourself so low that that the power per core is in this range. You would rather just drop off some cores and put it at the peak efficiency somewhere here. And if you add too many cores, like I said before, you end up having to reduce the power draw per core, and you lose too much performance, so you lose efficiency because you're just you have to sacrifice so much clock speed to get a small decrease in power. So if we take Van Gogh at 9 watts, for example, and this would be, you could probably put this in a tablet, for example. Now we have an assumed on-core power. We take the same for that, 3.5 watts, because the GPU, of course, always has to be running. The Infinity Fabric is going to be running. Maybe this is going to be a little bit smaller for Van Gogh because you drop the CCX. Maybe RDNA is a bit more efficient. Who knows? But if we assume the same 3.5 watt figure, we have a remaining core power of 5.5 watts, and with 4 cores at 5.5 watts total, we end up with the calculated core power of 1.375 watts, which is surprisingly close actually to the Renoir 15 watt figure. So if we assume Renoir is operating at an efficiency level AMD is happy with, Van Gogh at 9 watts, with 4 cores is going to be the same. If we took Renoir, for example, and reduced it to 9 watts and assumed the same on-core power, we'd end up with only 0.7 watts, and I expect quite heavily that this will end up somewhere in this static power dominated regime where you're just losing efficiency because you have to clock it too slow. So, what to conclude then, what is the purpose of Van Gogh? Well, in the die area analysis, we essentially covered that the die area saving is not very small. So it's not going to be a cheaper APU to build in terms of the die area cost. In terms of power, I think this is quite an interesting APU. We have, we're looking at a 9 watt APU with around the same per core power consumption as Renoir. Seems like to me that if this is going to be mass produced for for OEMs to use, this could be an interesting thing to put in tablets. The alternative, I think, is that maybe someone is looking to make a specific device, wants a 9 watt APU to put in it, and AMD is filling that gap for that customer essentially. So not really a hard conclusion, but overall it seems like Van Gogh is really targeted towards this this 9 watt power class. If you like this video, make sure to give it the thumbs up. If you have comments, questions or something in the that can go down in the comment section below. I have a Patreon now. If you want to support me, you could support me there. And I'm looking to do some more overclocking content soon, but you never know with university. There's a lot of stuff to do, and it's not always predictable when I'll have time or not, but it is what it is. So yeah, I'd like to do some memory and motherboards soon, but who knows when that'll be. So I will see you in the next video then.